Greetings, physicists. This video will be about how to solve problems involving the energy in a simple harmonic oscillator. So, we'll start with some astronaut stuff. When you're in free fall, you can't just stand on a balance because, you and the balance are falling at 9.8 toward the center of the Earth. So, being weightless is hard. It's hard to measure your mass, but it's important, right? If you're going to spend a lot of time in space, you got to monitor your vitals. So what they do is, this is kind of interesting. Let's see, I think I have a picture here that I'm going to try and copy, but of course that's hard to do. But you sit in a special chair, you like strap yourself in, and this is a simplified version, but if this is the wall, the chair attaches to the wall with the spring, and someone pulls you back, and so you oscillate back and forth on the spring. And then you can measure the period of the spring, or the frequency of the spring. So apparently this astronaut here is losing mass every day, and it goes down steadily. We assume that's probably a constant decrease then. And so when she gets onto this chair each day, what happens to the period of her motion? So let's look at that. So the period of spring is equal to 2 pi square root of m over k, yes? 2 pi square root of m over k. Yes. So what we see then is that t is directly proportional to the square root of m. So if her mass is going down, that's a direct relationship, so the period should also be going down. So if she were to lose, I hope she doesn't lose half her mass. I'm picking that because it's, well, let's say she loses a fourth of her mass. That's not much. If she were to lose a fourth of her mass, the square root of a fourth is a half. So her period would, her oscillation would take half as much time. But that's the period, right? The period would be 2 pi squared of m over k. The frequency is the inverse of that. So the frequency should actually go up. She should go back and forth quicker on that chair as she loses mass. Okay. All right, we got a spring, vertical one this time. We're going to hang something from it. And they tell us the difference between the equilibrium of the spring without the mass on it and the with the mass on it. And they tell us the mass itself. And they ask if the mass is pulled down, what is the new frequency? So the frequency of a spring, 1 over 2 pi square root of k over m. Now we have m, we need k. So k, we have this equation, right? The force, the spring force, is equal to kx. So let's think about this. We have the spring here unstretched, and then we have the spring with the 25-gram mass on it. That distance, that difference, right? So that was, if this was a 10 centimeters, and this is a 15, then that difference is 5.0 centimeters. So we have x, and the force then, well, we need a free body diagram. Well, the force then is mg down and spring force up, and we're assuming this is at equilibrium when they add the mass to it. So those are equal, so I can say that mg equal kx. I'm going to divide by x and get that. And I can plug that in, up here for k. So the frequency will be equal to 1 over 2 pi times the square root of, instead of k, it's going to be mg over x, and there was already an m on the bottom. So the frequency of that spring, in this case, our mass will cancel. Okay. Does that always happen? That seems wrong. Well, let's just keep going and see what we get. That would be 1 over 2 pi square root of 9.8. That's meters in seconds squared divided by x, which is in centimeters, so I'm going to make it in meters, 0.05 meters. All right, let's see what the calculator wants to tell me. Okay, 1 divided by 2 pi. And do the square root of 9.8 divided by 0.05. Okay, well that is the right answer. Oh. So I'm getting 2.2 hertz. Okay. I think what's confusing me, sorry, what I'm looking at this is, I know that the frequency does depend on the mass, but the force is based in this case on the mass. However, what would happen is, what would change about this is if that mass were increased, even though it cancels here, it would not, it would change the stretch, right? So if I put a bigger mass, if I put a 50 kilogram or a 50 gram mass on there, it would stretch 5 more centimeters. So this x would change, and that x is a function of mass. So that should make sense. All right, I satisfied myself that I'm not going crazy. All right, 2.2 hertz, good stuff. Keep going. Volt. This used to be my favorite thing to watch. It's so quick. Looks really hard to do. So if you watch vault, they have only the females do it. There's no like male version of the vault. So the gymnast like running, and there's this like springboard here, and they bounce off of it, and then there's like a big platform up here, and they put their hands on it so that they like jump. And then they like end up here, and they do a bunch of spins and stuff, and then they land. Really dangerous too, I think. I remember one girl getting badly injured one year. All right, so here we know it's a 45 kilogram gymnast. She jumps into the air. So when she jumps from here, she jumps up. And at that point, she is 0.60 meters above the top of the springboard. Then she lands on it. And that's the only part that we actually care about. How far does it compress? So from like here, the springboard's going to compress under her weight. And we know the spring constant of the springboard. So we're looking for the maximum compression, which is the distance. And we're looking for time. Tricky. So when you deal with vertical springs, and I'm going to simplify the picture, but essentially this is kind of like this. Here's the unstretched spring, and the person up here, they're a height above the spring. And in this case, that height is 0.60 meters. So we'll call that h. They land on the spring, and I'll draw that over here, and it compresses until they're standing on it, and now they're down here. The mistake you don't want to make is this one. You cannot say that mgh is going to be equal to half kx squared. That is the trouble that people get into with this. And the reason you can't say that is she falls mgh to here, but then she falls a little more. There's more height to be lost because the spring is compressing vertically. So there's this like delta. This is like the equilibrium position and then the final position. So this is the delta x, right? That's this. That's how far the spring is compressed. How much gravity energy does she lose? She actually loses all this, which is h and x together. So when you do your energy equation, it looks like this. She loses this much mgh. She loses mg, and I'm going to put parentheses h plus x. That's how far she falls. All of that turns into, by the end, half, not mv squared, it's half kx squared. And we should notice that the two places we are comparing are up here where she's at the peak of her jump, so there's no velocity upward or downward, so the vertical velocity is 0, so there's no mv squared there. And at the bottom, when she's compressed this thing fully, it comes to rest, so there's no mv squared there. So we don't have to deal with kinetic energy in this equation, which is helpful. All right. So when I distribute this on the left, I'm going to get mgh plus mgx equal to half kx squared. And we're looking for x. And we have an x. We have an x squared. This is a quadratic equation. And there's really no way around that. You're just going to have to do a quadratic. So let me move everything to one side. 0 will be equal to half kx squared minus mgx minus mgh. Now we know her mass, we know gravity, we know h, the height that she started above the springboard. So, and we know the k. So those are, for our purposes, those are all constants in terms of solving the quadratic equation. So everybody has their own mnemonic for solving the quadratic equation. This is the one I happen to learn. X will equal. So there was a negative boy who couldn't decide to go to a radical party. He didn't know there would be square dancing, so he lost out on 4 awesome chicks. And the party was all over at 2 a.m. There you go. Now we need to plug stuff in. I'm going to plug in the variables first. So this is A, this is B, this whole thing is C. So there's a negative boy, which was already negative, so that's mg plus or minus the square root of b squared, which is m squared g squared, minus 4a, which is half of k, c, which is negative mgh, all over 2 times 1/2 of k. Did I get all my numbers right? Or did I get all my negatives right? That's really what I need to know. I think so. This is squared, so they go away, and then there's a negative here and a negative here, so that'll be positive. Everything under the square root will be positive, which is good. Otherwise I get imaginary numbers. All right. Or can get imaginary numbers. So plug some things in. Her mass was 45 kilos. Gravity is 9.8 meter per second squared, plus or minus square root. Again, 45. To save room, I'm not going to put units in. So far, that's all in kilograms, I think. K was in newtons per meter, so we were fine there. Height was in meters. Yeah, we're good. All right, so 45 squared and 9.8 squared. I'm just going to put a plus because the negatives cancel. 4 times 1/2 is 2. So 2 times 50,000. Gosh, I'm out of room anyway. Times mgh. So keep in mind this is all being multiplied. Mass is 45. Gravity 9.8. And h is 0.60. I'm sorry, that's so messy here. And the party was all over at 2 a.m. 2 times 1/2 of k, which was 50,000. Oh, look. That'll cancel. Okay. All right, plug that into your calculators. And we get 2 answers, right? Because it's plus or minus. And the plus value we get is 9.4 centimeters, and the minus value that we get is 11.2 centimeters. What do we choose? Well, we have to go back to our picture, because our picture is based on this. This is the key, the height. The height was 0.6 meters. From where? Well, it was from where she was in the air to the top of the spring unstretched. So the spring is the reference point. That's 0. That's 0 meters. Where does she end up? Below 0. So we do end up in the negative direction from the 0 point, which is the top of the spring. That's your key. So because we end up below the spring, that's minus 11.2 centimeters. All right. That's a tricky one. Now that's only half of this problem. The other one says, how long does it take the spring to compress? So from the time when it's here to the time when it's here, how much time is that? Well, that at first that seems like a big deal, but what we're going to do is say that, think about it, this was equilibrium, and this was max amplitude, A. So we can do the period, we can do the period of a spring and say that this time that it takes is actually, well, let's see, it would go from here, down, back up, and back to middle. That would be one period. So this is a fourth of a period, is the time it takes that spring to compress. Because once she lands on it and it starts to compress, she's in simple harmonic motion. She doesn't finish simple harmonic motion. She gets launched off of it before she finishes a whole period. But for that quarter of a period, she's in simple harmonic motion. Well, we know the period for a spring. So let's look at that. The period for a spring is equal to 2 pi square root of m over k. Well, I have a fourth of that, so let's just divide it by 4. So that's equal to pi over 2 times the square root of her mass, which is 45 kilos, divided by k, which is 50,000. Which is very small, because that's a big number in the denominator. So if you plug that into your calculator, 0.047 seconds, and we are 2 sig figs. I mean, that's not almost half a second, that's almost half of a tenth of a second. So you watch these videos and they land and bounce and they're off. I mean, it would take that time to compress the spring. It would take double that time because she has to come back up off of the spring. So the total time she spends on the springboard is almost a tenth of a second, but not quite. So there you go. Very stiff spring. All right, let's do one more. I think. Yes? Do we have more? Yes. Okay, that was a long problem. Grandfather clock. You may have seen these, right? Here's a grandfather clock. It's a big, tall thing, and it's got the face of the clock here, and there's a window below it with this big pendulum that swings back and forth. And that pendulum is connected to the gears that wind or that move the hands of the clock, so it uses gravity instead of electricity, which is kind of neat for those of us trying to lower our carbon footprint. Of course, you got to wind it because there's a big spring inside, and when the spring runs out, it no longer keeps time. All right. The only thing they give us is that it's 1 second, and they say what is the length of that pendulum. One swing, and this is key. They say 1 second, but that's one swing of the pendulum in either direction, meaning that if it starts on the right here, it swings to the left. That's it. Keep in mind that's half of a period. Period of a pendulum. So we have a period of a pendulum is 2 pi square root of L over G, but we're doing half a period, so we got to divide it by 2. So that would cancel. So the period of this pendulum will be equal to pi times the square root of the length. Oh, sorry. Pi times square root of L over G. Let's solve that for L. So I'm going to divide by pi. I'm going to square everything. And I'm going to multiply by G. And that should equal L. Okay. So the length of this pendulum is t squared. So t was 1 second. So 1 second squared on top over pi squared times g, which is 9.8 meters per second squared. Oh look, second squared cancel. That's awesome. So my length will be to 3 sig figs, actually, 0.993 meters. Now, if you were to round that, you would get 1 meter. This is actually one of the earliest definitions of a meter. Some British guy, I forget his name, John something. They were all named John. He wanted to define what a meter was. So he said, here, take a piece of string. Just cut a piece of string. Attach a little rock to the end. Doesn't matter the mass, right? Mass is not part of the period equation. And hold it. So here you are holding your string with your rock. And just let it swing back and forth. When half of a period is equal to 1 second, you have a meter. Or, in other words, a pendulum with a 2-second total period has a length of 1 meter. Or at least that's how he wanted to define what a meter was. We've come up with other things since then for how long a meter is. I think right now it's defined by a fraction of the speed of light. Or the amount for a certain amount of time. But this was fairly accurate back in the day. I mean, you know, and when I say back in the day, this is probably about 400 years ago or so. So 400 years ago, if you were off by, I guess this is accurate to 2 sig figs, that was decent. They would have accepted that. So not terrible. And a little history for you there. All right. Hopefully this helps you in solving energy and simple harmonic motion.